Hello everyone, my name is Wong Zhenyue. Today I will introduce the multivariable mean value theorem. Okay, before we start, let's have an overview first. In this video, I will talk about why we need the multivariable mean value theorem and the main idea behind the proof. Then in the last, I will talk about why the theorem cannot be generalized to multivariable function. So let's start from single variable function first. Single variable mean value theorem says that let the function f satisfy the following condition, which is f is continuous and f is differentiable. Then there might exist a point C in the open interval a b such that f prime or c equal to f of b minus f of a over b minus a. But we don't know what this equation means. So that a picture, we can easily see that the mean value theorem just means the slope between two endpoints must equal to the slope of the tangent line for some point C equal to inside the interval AB. And then why we need the multivariable mean value theorem? Because in single variable function, the mean value theorem is one of the most important theorem in analysis, and mean value theorem plays a key role in proving many theorems. Okay, for example, we know the constant function must have zero derivative, but for the reverse statement that a function with zero derivative must be constant is not quite obvious, and we need to prove this lemma using the mean value theorem. Therefore, we wish to extend this useful theorem to higher dimensional. But before we talk about our main topic today, let's talk about the relevant theorem first, which is the chain rule. Chain rule says that if the function f is differentiable at s0 and the function g is differentiable at y0, we define the y0 equal to f of s0, then the composite function hash from O to Rn is differentiable at s0 also. And we have the Jacobian hash of s0 is equal to the Jacobian gf s0 multiply the Jacobian f of s0. Then why we talk about the chain rule? Because we want to use it later in my proof. Okay, so now we talk about the multivariable mean value theorem. This theorem says that let O be an open subset for Rn, and let S0 and S0 plus hash these 2 points be inside this open set O, such that the line segment between these 2 points must lies entirely inside. Then if the function f from O to R is differentiable, then that must exist a constant C in interval 0, 1 such that we have the following equation, which is f of s0 plus hash minus f of s0 is equal to the dot product of gradient f of s0 plus ch and hash. And we can express the dot product, we will get the following summation. And before we start our proof, let's talk about the idea in this proof. I will change the problem from multivariable function into single variable function. And then we can apply the mean value theorem we're familiar with, which is the single variable one. So we start from define a function gamma from closed interval 0, 1 to Rn. Then by gamma t equal to s0 plus th. So we can see that the gamma 0 is equal to s0 and gamma 1 equal to s0 plus h. And note that the function gamma is differentiable with gamma prime t equal to h. Since it's just a affine function, then now we can define the function g, the composite function. We composite the function f and gamma. Then g is from closed interval 0, 1 to r. And we have the following, which is gt equal to f of gamma t. And we apply the gamma t, we will get gt is equal to f of s0 plus th. Since f and gamma are differentiable, then the composite function g is also differentiable. Now we can apply the chain rule to calculate the G prime. So G prime is equal to the Jacobian f of gamma t and multiply the Jacobian of gamma t. But now we just live in one dimension. So it's same as the dot product of f of s naught plus t has the gradient and gamma prime t. And just now we know the gamma prime t is equal to hash. So the dot product is like the following. And then since the function g is differentiable and continuous, we can apply the mean value theorem for single variable function. So they might exist a point C inside this interval 0, 1. So we have g prime C equal to g1 minus g0 over 1 minus 0. And from this, we will get that the g1 minus g0 is equal to f of s naught plus hash minus f of s naught. But just now we also say that g prime t equal to the dot product. So just now we change the t variable to c. So we get that f of s naught plus hash minus f of s naught is equal to the dot product gradient of f of s naught plus c hash and hash. And we can express it like the summation. So actually this is what we want to show and we are done. But before we end, I will give some remark first. The mean value theorem only works for m equal 1 for the codomain Rm, this multivariable function. It cannot be generalized to the function like from Rn to Rm if m greater than 1, because in higher dimension for each coordinate it may behave differently, so the total change is no longer guaranteed from a single Jacobian only, but it's not quite obvious. So let's give an example to show why the mean value theorem doesn't work. So the example says that let the function f from R2 to R2 and we define by f of sy equal to s squared y and sy. Now we take s not equal to 0, 0 and h equal to 1, 1. Okay. Note that the Jacobian f of sy is equal to this matrix. When s not equal to 0, 0 and h equal to 1, 1, and the function f is differentiable, then there might exist a constant c in 0, 1. We apply the mean value theorem here. So we have the s naught plus ch equal to cc such that f of s naught plus h minus f of s naught is equal to the Jacobian f of s naught plus ch multiply the vector h. This h is come from the Jacobian s naught plus ch. So we have the following equation. If we plug in the value and we solving it, we will get that the 3c squared equal to 1 and 2c equal to 1. However, this is obviously we get the different c in these two equations, which is c equal to 1/2 and another is c equal to plus minus 1 over root 3. So there is no c can work for both equations. So the mean value theorems will fail in this case. So in conclusion, you can't expect that the single derivative will perfectly match the average change from point A to point B. That's why the general mean value theorem like single function cannot work here. And therefore, even though the multivariable mean value theorem is quite useful, but it still have its limitation in higher dimension. And this is the reference I use, is the Professor Developing Mathematical Analysis Volume 1 and the Mathematical Analysis Volume 2. Just now the non-example is from this Volume 2. And that's all for my presentation. Thank you for your watching.